Mm, I would like to take it like this. So let this be a spherical surface. Now, what are the points that we have to think of? First of all, this let this be the pole, or and then you have the center of curvature where the compass center was placed, so that your center of curvature, and hence you have a radius of curvature r. So these are the only things. The other things you know is the refractive index of the two media. You know the refractive index of this first medium n1 and this refractive index as n2. Now the ray of light, it may enter either from n1 to n2 or it may enter from n2 to n1. Okay. So how the formula is to be applied? See, if you have any object which is placed, let's say you have an object which is placed at this point O. So if you have an object which is placed, so here let this be point O, you have placed an object. Now we consider two rays of light which move from this O. So one of the ray of light, it passes along the principal axis, so it passes undeviated. The second ray of light, it passes at any angle. Let's say it passes at a certain angle alpha. So if it passes at a certain angle alpha, now we will find its bending. So where will it bend? For that we draw our normal. So this is our normal. Let me draw the normal now. So from center of curvature, if you join, this will be the normal to the surface. Now the ray of light was expected, this ray of light was expected to go like this. It was expected to go like this, but it will show some bending. Here, if we consider, it's up to us, we are considering that N2 is greater than N1. So for this case, we are considering N2 is greater than N1. So the ray of light which is passing by, it shall bend, it shall bend towards the normal. So the ray of light here, it bends towards the normal and hence passes something like this. And maybe it touches the principal axis at some point I. So at this point, you will have the formation of image. And image I will be formed at this point. Okay. So this formula, the formula which relates both of them. So currently for this diagram, we have taken N2 is greater than N1. However, if the it can be that N1 is greater than N2. Okay. So we have the formula N2 by V minus N1 by U is equal to N2 minus N1 by R. So this is the formula for refraction at the spherical surface. Now let us see the definitions clearly. Here N1 is the refractive index of the medium from which rays are incident. So it is the refractive index of medium from which rays are incident. Rays are incident. So from wherever the rays are incident, that medium will be taken as N1. So if suppose everything is the same, but the range of light, they are moving from N2. So you will just exchange the values of N2 and N1 in the form. Okay. So now you will be start considering the other way. We'll see some of the some questions if possible. So this is the formula. N2 is the N1 is the refractive index of the medium from which rays are incident, and N2 is the refractive index of the medium. N2 is the refractive index of medium in which lights are entering, in which light enters. So the medium in which the light enters, that is, it's not, N2 is not the a medium where the image is formed. N2 is the medium where light enters. So maybe it may happen that image is also formed in N1. It can happen sometime that if there is no sufficient refraction taking place. Suppose if the refraction occurs like this, so you will have the formation of image in N1. Okay. So N2 and N1, they are defined on the basis of where the light rays are coming and where the light rays are entering. V is the image distance which will be measured from pole. U is the object distance, again that which will be measured from pole. And R is the radius of curvature. So R stands for the radius of curvature. Again here we will be considering our sign conventions according to the rule. Like if the rays of light, they are incident like this. So the direction of the incident light will be taken as the positive direction, and the other direction or the direction opposite to it will be taken as the negative direction. So if in this situation, if I measure the object distance will be measured as negative from pole to O, that is opposite to the direction of incident light, that will be negative. If I measure the radius of curvature here, that will be positive. If I measure image distance, that will be positive. Sometimes it can happen that the radius of curvature is negative. Okay. If suppose if the ray of light enters from N2 to N1, so in that case we will be having radius of curvature to be negative. So every time while applying the formula, we must check the sign conventions. Now the next one is the lens maker's formula. So the lens maker's formula is also related something like this only. So lens maker's formula, let's see. Lens maker's formula. So lens maker's formula, it relates the refractive index with radius of curvature for a given lens. So using the lens maker formula, it states thus that N2 by V, again the same thing, N2 by V minus N1 by U is equal to N2 minus N1 multiplied by 1 by R2 minus 1 by R. 1 by, it's I think 1 by R1 minus 1 by R2. Let's have a check. Yeah, it's 1 by R1 minus 1 by R2. Okay. 1 by R1 minus 1 by R2. And here both are the refractive, here both of them, they are the refractive index. You have both are the refractive index of medium one. So you can write it as N1 by V minus N1 by U equals N2 minus N1 multiplied by 1 by R1 minus 1 by R2. So this is how this should be remembered. Here again, N1 is the medium from which the ray of light is entering, and N2 is the medium, that is the lens. N2 is the refractive index of the lens. R1 is the first radius of curvature, and R2 is the second radius of curvature. So this can be rearranged with the terms. N1 can be taken common, and you will have 1 by V minus 1 by U equals N2 by N1. So N2 by N1 will be refractive index of 2 with respect to 1. So that refractive index of 2 with respect to 1 minus N1. Sorry, N1 by N1 will become 1. So you have n minus 1, and you can write 1 by r1 minus 1 by r2. So this is the formula you can remember, but I think as soon as I speak, this one is the best way to remember, best thing to remember it, because sometimes if you are given that lens is dipped in water, so if lens is dipped in water, so instead of n1 you need to put the refractive index of water. Okay, and instead of n2 you need to put the refractive index of lens. So either you do that way, or you should be very well aware how to find out the relative refractive index. That means how to get the relative refractive index of 2 with respect to 1. So n21 can be obtained as n2 by n. Sorry, n12 can be obtained as n2 by n1. So it will be n12 means refractive index of medium 2 with respect to 1. So find that. Okay. So, and the same thing, this whole thing is equal to focal length f. So you can also write here that the focal length f or 1 by f will be equal to n2. This is n12 refractive index of medium 2 with respect to 1 minus 1, and here you have 1 by r1 minus 1 by r. This is the formula of refractive index of focal length of a lens. So the lens maker's formula stands like this. You can find out the focal length of a lens by using the refractive index given to us. We can obtain its focal length and radius of curvature. Okay. So anyone having any doubts here? If the okay, what if you suppose you have a convex lens? If you have a double convex lens, and for the double convex lens, I get R1 equals to R2. So what should be the focal length then? Okay. So what value we will get for the focal length? Can you simplify the expression? If I get R1 equals to R2 for this double convex lens, as you have seen a double convex lens. So for a double convex lens, what should be the relationship? How we will obtain it? See, this is the first refracting surface, and the radius of curvature of the first refracting surface is positive. So this is our R1, which is positive, and this is the second refracting surface, and the radius of curvature of the second refracting surface is negative. So this radius of curvature for the second one is negative. So if I'll put R1 equals to R2, let this be equal to R. So I'll substitute in the formula as 1 by F equals to N refractive index minus 1 over 1 over R, and minus of minus 1 by R. So it will make 1 by R plus, and hence you will get 2 by R. So you get 1 by F equals N minus 1 multiplied by 2 by R. So this is the relationship that we own for a double convex lens. What will happen to the, okay, on this basis, can you tell what will happen to the focal length of a convex lens if it is placed in water? If a convex lens is placed in water, so what will happen to its focal length? Yes, any idea? Javier, Srivita, can you tell?
No, sir.
See, when you place a lens in air, so if a convex lens is placed in air, so it suppose it has its focal length as f. Now, if the same convex lens is placed in water, so the relative refractive index for the lens will decrease. The value of n will decrease, and hence the value of the focal length will increase. So it's something like this. If you have a lens over here in air and it has its focal length somewhere, so that you get these all the ray of light and they meet at certain point here. Now, if the same lens is placed in water, so the same rays of light which are parallel, if I get some rays of light which are parallel, so now the rays of light will take a longer distance to meet because there will be lesser refraction which will occur. The relative refractive index will decrease. So there will be an increase of focal length. And then what will happen? What will happen if the refractive index of the lens and the surrounding medium is the same? Then can you guess what will happen if the refractive index of both the medium is same? Whatever is the refractive index of the lens, the same is the refractive index of the surrounding material. So will there be any refraction taking place?
No, sir.
No. Then there will not be any refraction taking place. In fact, you will get here the relative refractive index as 1 and 1 minus 1 would be 0. So you will get the value of focal length as infinite. So focal length would be infinite. That means the rays of light will never meet and there will not be any refraction that occurs. Now, what do you think if I have this N1 and N2 as the lens? So if N1 is greater than N2, then what will happen? Suppose water or whatever material in which the lens is put up. So if that has a higher refractive index as compared with the lens. So yes, what do we expect then? Will there be refraction? If N1 is or the refractive index of the surrounding medium is greater than the refractive index of the lens, so in that case, still there will be refraction, but the lens will start behaving as a concave lens. The same lens will start behaving as a concave lens, and there will be diversion occurring. You will be getting a focal length as negative. You will get this value of focal length as negative. So which will mean that this lens will start behaving as a concave lens in that medium. Got it? So these were some of the important points which were related to refraction of light. And okay, so the next you can get some questions from transformer. So see, for the transformer, that is in electromagnetic induction, you have this topic of transformer. So some things you need to remember about the transformers. So first of all, tell me, is transformer an AC device or a DC device? Yes. Does transformer work on an AC circuit or a DC circuit? And
AC.
what is AC circuit? So can it also work for a DC circuit?
No, sir.
A transformer cannot work for a DC circuit. It can only work for the AC circuit. So here we put two coils. This is your primary coil P, and here you have the secondary coil. So the whatever magnetic field is created in the primary, that magnetic flux is linked with the secondary. Okay. So the magnetic flux of the primary gets linked with the secondary. There is no direct flow of current from P to S, but the magnetic flux that is linked with the primary gets linked with the secondary. So there will find a changing magnetic flux through secondary, and